Well, welcome. It is Tuesday, April the 6th here at Advanced Level Chemistry at Spring Park. Yesterday we went through and started talking about gas laws. Had some groovy demonstrations, with trying to make a demarshmallow, and we had shaving cream kind of just going everywhere, balloons popping, Chick-fil-A balls bursting, okay? All to demonstrate these three laws, okay? Whereas Boyle's law is a relationship between pressure and volume. Okay, make sure we're seeing this up here, okay? Boyle's law, temperature is constant, it's relationship. What type of relationship is that then, a direct or inverse?
Inverse.
That's the first one, inverse. Inversely proportional. Charles' law is volume and temperature. What happens if you increase the temperature to the volume? You just go up or down?
It goes up. As the volume goes up.
If you increase the temperature, the volume is going to increase. So if I put this balloon into a warm area, it's going to get bigger. Things expand generally when they're heated. That is a direct proportion. And then pressure and temperature, keeping the volume. Now, pressure constant is like a balloon, where the balloon's allowed to expand to keep the pressure the same on the inside. A volume is constant like that, a can, like a aerosol can that can't expand. So this also is a direct proportion. And we can plug in here. Pressure, we've talked about all the different units pressure can be measured in. Volume can be measured in milliliters, liters, gallons, quarts. But what unit does temperature have to be?
Kelvin.
Kelvin. And just remember that temperature, or let's just say this, Kelvin is equal to degrees Celsius plus 273. Make sure that you have that down somewhere in your notes that you know that. It's a simple conversion. Okay? So if we look on two thermometers, and we talked about this, I think, earlier in the year. Two thermometers, 0 degrees Celsius. 0 degrees Celsius is going to be what Kelvin? 273. So 100 degrees is going to be 373. So what's the difference in a degree? How many divisions are there between freezing point, boiling point on Celsius? What about on Kelvin? 100. So what about how the difference between a 1 degree Celsius and 1 Kelvin? They're exactly the same. It's just the 0 point. This, down here at the bottom, is absolute zero, which is negative 273. Negative 273.15. Okay? So the only thing is the 0 point. So if anything is ever delta T, change in temperature, it doesn't matter whether it's Celsius or Kelvin, but in an equation where it's just temperature, it has to be Kelvin.
What would happen if like something hit the 0 point or
This right here, absolute zero. Now first off, it's impossible to reach, but this is where we read about that Bose-Einstein condensate, to where all the particles collapse and act like one superparticle. But the reality is just, on the simplest definition, is that all vibratory motion stops. Everything is perfectly in place. Zero entropy. Okay? So, these are our three gas laws. Now, we have Boyle's, Charles, Gay-Lussac's, all these guys. Well, a guy named Mr. Combine came along, and he decided, I didn't do present. He decided that he'd like to, put everything all together. We did all this already. This is where we ended up with Gay-Lussac doing these. And this is all, again, on Classroom for you. now to the combined gas law. Now nothing is held constant. This is really the only one that I remember, that I've tried to remember, combined gas law. Because if I'm looking at this one, if I keep temperature constant, I get Boyle's law. If I keep pressure constant, I get Charles' law. If I keep volume constant, they cancel out, I get Gay-Lussac's law. If nothing is held constant, I have to use all three. Now notice that you're given an initial pressure and a final pressure, initial volume, final pressure, two different sets of conditions. And that's going to be important as we're trying to figure out which one we're going to do. Okay, that's just cross multiplying. Okay, temperature must always be in Kelvin. Nothing changes. Okay, so here's an example. Notice we have it has a volume, a temperature, and a pressure. What volume will it be at a new pressure and a new temperature? Well, I mean, you just plug in P1, V1, V1, T1, P1. We're looking for V2, P2, and T2. Now, what's the only thing we have to do with temperature? Convert it to Kelvin before we plug it in. So go ahead and plug it in and see what you get. So we got to be able to do a little bit of algebra in order to be able to isolate the volume. Okay? My initial pressure, we're going to go P1 V1 over T1 is equal to P2 V2 over T2. Okay? So my initial pressure, you need to be able to recognize that atmospheres is pressure. My initial volume is 50 liters. My initial temperature is 25. What's that equal to? 298. That's one that you should just, 25 is a very common. Is equal to the new pressure of 0.855 atmospheres. We're looking for the new volume, and the new temperature is 283. Okay. So how do we isolate V2?
Simplify the left first, yeah. Multiply 283 and find out 0.8.
Okay, so the reality is that this is going to come up here, and this is going to come down there, right? Hopefully you guys can see that algebraically without cross multiplying and then dividing back and doing all that. Okay, so we end up with 283K times 1.008 atmospheres times 50 liters divided by 298K times 0.855 atmospheres. Is everybody comfortable with that algebra? Fairly basic. Now notice, kelvins will cancel, atmospheres will count, leaving me liters. So whatever unit the volume is on the left side, that's what it'll be on the right side. If this was milliliters, it'd be milliliters. If it was quarts, it'd be quarts. And what does the answer come out to, the three sig figs? 60.0 liters. Okay, so it's going to go from 50 to 60 because you're decreasing the pressure. Now you're decreasing the temperature, but you're decreasing the pressure as well. So one's making it bigger, one's making it smaller, but obviously the decreasing pressure had a greater effect. All right, so nothing's held constant here, but these are all just plugging in. Okay? But notice what they don't tell you anything about. Do we know how much is there? Moles or grams? No. We just know the relationship. Once we have a closed balloon, I just know, okay, so I have a certain number of molecules in here at a certain pressure, temperature, and volume, that if I change those conditions, I put it into a vacuum and change the pressure. I put it into an ice bath, change the temperature, okay? Then I can, change the volume of the container. I can change the pressure on the inside. I can change the conditions. But I don't really know how many molecules are in here, just given this stuff, okay? But notice again on these problems, you're always given two sets of conditions, all right? Because we need to know quantity. What do you think happens to the volume if you put more gas into a balloon? Does it get bigger or smaller? Bigger. More molecules, more volume. What happens to the pressure? More pressure, right? So those are all directly proportional. So volume and pressure and moles are all directly proportional. Now changing the temperature doesn't change how many are there. It changes how fast they're moving, but it doesn't change how many. But changing the number changes the volume and the pressure. So there's just going to be the answer to this one. 60.0. We already knew that. Okay? Here's another comprehension check. If you want to do more practice, you can do that one on your own. So here's just a table of everything we've talked about. What's held constant in the relationship. Okay? So that's basically what I have on the board right there. All right, we're not going to do those. So let's talk about this ideal gas law. We have Boyle's law, Gay-Lussac's, Charles' law. Here's Avogadro's principle. Avogadro, same as 6.02 times 10 to the 23rd guy. Now again, Avogadro did not come up with that number. Some other Italian guy did and named it after Avogadro. But Avogadro did come up with this. And this is probably his greatest accomplishment. Equal volumes of gases at the same temperature and pressure contain equal numbers of molecules. So I have two balloons that are exactly the same size. They're at the same conditions of temperature and pressure in this room. I can say that if this is hydrogen gas and this is oxygen gas, there's still going to be the same number of molecules in each one. Because gas molecules are so tiny, the volume occupied by the gas is really mainly the space in between the molecules, not the molecules themselves. There's plenty of room. It's like when you go to Bryant-Denny Stadium, nowadays when they only let 20,000 people in there. It doesn't matter if it's a big person or a small person, there's room to spread out. Okay, and so you can spread out, you can fill up the whole place, and there's plenty of space. It doesn't matter how big or small, but when you get crowded, when it's jam-packed back in the day, and the seats are about this wide that on the benches that you're allowed to sit on, your numbered seat, and somebody that's about this wide sits next to you, then the size matters. Okay, and so people always hope when I'm walking up there, oh, don't let him be sitting next to me. It's kind of like on a plane, when you have that middle seat open, and you're saying, oh God, please don't let somebody sit in that middle seat. Avogadro's principle, equal volumes of gases contain the same number of molecules. Now that's going to be very important, okay? Doesn't have to be at any particular, as long as they're the same temperature and pressure, we're going to have the same number of molecules. So that brings us to the ideal gas law. And the ideal gas law is PV equals nRT. Pressure, but this time R is a constant, and it's calculated in these units, so pressure has to be in atmospheres, volume has to be in liters, N is always moles, R is 0.0821, and T is the temperature, always in Kelvin. This equation, notice we only have one set of conditions. With one pressure, volume, and temperature, I can know how many moles are present. That's going to be very important for us, especially trying to do stoichiometry and that kind of stuff. Woo! You love that S word again, stoichiometry. Gas law, stoichiometry, coming up next. Get fired up, yeah, that's just enough to just get your blood pressure just going a little bit. PV, PIV, PV equals nRT. Now we're going to talk about an ideal gas in a little bit later, but when we're looking at this, here's an example. What is the pressure in atmospheres exerted by 0.5 mole of a sample of nitrogen gas in a 10-liter container at 298? Now, I know that I want to use PV equals nRT for two reasons. How many different pressure, volumes, and temperatures? Do I have an initial pressure and a final pressure? No. Just one set of conditions, right? One pressure, one temperature, one volume. That's the first clue that it's going to be just an ideal gas law. The second one is you're talking about moles. If moles or grams are ever given, then you're going to be using the ideal gas law. This one is the one more, in AP chemistry, pretty much this is the only one we use. It really is ideal. It does everything for you. Okay? So when we plug that in, PV equals nRT, N is 0.5. R is always 0.0821, that number is given to you, you don't have to memorize it. Temperature, we changed 298, and the volume is 10 liters. So the pressure is equal to nRT over V, and you end up getting 1.22 atmospheres. Now, we can calculate all kinds of stuff from this ideal gas law. Okay? Now, you guys are all taking notes, which is great because I didn't make a slide because it was too hard to type all this. So, but if we have, these are rearrangements of PV equals nRT. All right. So the first one is we have PV equals nRT. But how do we, if we're given grams, how do we convert grams to moles? Molar mass, right? So we could say that PV is equal to grams over molar mass RT. Because grams divided by molar mass is moles. Now, doing math, algebra, solving, isolating molar mass in the numerator, getting it up. Multiply both sides by molar mass, and then bring pressure and volume back down over here. Molar mass is equal to GERT over PIV. So we can calculate the molar mass of a gas if we know the grams, temperature, and pressure and volume. Now this is all still the same equation, I'm just rearranging it. Okay? Now, but G over V is equal to mass over volume, which equals, mass over volume is what? Density. So we could say then, G over V, we could say molar mass is equal to dirt over P, or dirty P. Now, at STP, okay? We don't know what STP is, do we?
Standard temperature and pressure.
Did you, I talk about that, or did,
Just
We
kinda
talked about
I
it.
brought it up?
Yes.
Okay. If we have 1 mole of a gas, if it's at standard temperature and pressure, okay? Pressure is 1 atmosphere, temperature is 273. When you go and you multiply 0.0821 times 273 and divide by 1, that comes out to 22.4. That's the volume occupied by 1 mole of any gas at STP. Remember, Avogadro's principle says equal volumes of gases contain the same number of molecules. The converse of that, same number of molecules will occupy the same space. So if you have 1 mole of any gas, hydrogen, helium, nitrogen, oxygen, carbon dioxide, 1 mole of any one is going to occupy 22.4 liters. How big do you think 22.4 liters is?
A lot.
Think of a 2-liter soda.
Fill the size of that table.
Okay, fill the size of that table. That's kind of what I would think too. Going to my magic closet of science. There it is. This is 22.4 liters. Okay? It's about 1 foot by 1 foot by 1 foot. And I did the measurement, I double checked it, but it really is. Okay? So 1 mole of a gas at STP, 1 atmosphere and 0 degrees Celsius, would occupy a space about this much. But if I had this box full of helium, this box full of carbon dioxide, this box full of oxygen, this box full of any gas, there would be the same number of molecules if they're all at STP. That's Avogadro's principle, but the practical application of that is 1 mole at STP is 22.4. So, at STP, RT over P is equal to 22.4. So, that makes molar mass is equal to density times 22.4. Now, just so you know, density is equal to grams per liter. And then 22.4 is liters per mole. So if I multiply grams per liter times liters per mole, what do I get? Grams per liter times liters per mole. I get grams per mole, right? Which is molar mass. Amazing.
One more class we take, man.
So all of these are just rearrangements of that ideal gas law. Different things that we can calculate given pressure, volume, and temperature. Okay? So we have 1, 2, 3, 4, 5 variables and a constant. You'll always be given 4 of them and have to find the 5th one. It all depends on which one. But again, knowing that grams over volume, is density, these two are really the same equation. So if the density of a gas was, say, 1.75 grams per liter, you could either put that in right there as 1.75, or you could put 1.7 grams over 1 liter there. So you can use either form. Okay? So that's in your textbook. That's that thing in front of you. It's got a hard cover on it. Some of you might have looked at it at one point in your life, but this is actually your textbook.
Not one version of it, but it's kind of close to
Okay, and we're in chapter 11. I really just need to get chapter 11. We go to the end. I take this off and put my glasses on so I can. look at question number 73 on page 382. And it says, a gas sample is collected at 16 degrees and 0.982 atmospheres. If it has a mass of 7.4 and a volume of 3.96, find the volume of the gas at SDP and the molar mass. Well, let's do the molar mass first. What equation should we probably use in order to be able to find, what all are we given? We're given grams, volume, temperature, and pressure. Use the third one. Molar mass is GERD over PIV, right? Now, that's the same version. Now, technically, you could plug in the pressure, the volume, and the temperature and calculate moles. Okay? And then you can go grams divided by moles is equal to molar mass and do it in 2 steps. But I think it's just easier to plug in here. So go ahead and plug that in and see what you get. Do we have an answer? Stare at that for a while and just get that into your head. Okay, so what's the mass? What's G? 7.40 grams. R is always 0.0821. Now the units on that are liter, atmospheres, Kelvin, moles. R is always going to be the units of everything else. So when we solve for R, it's PV over NT. So pressure, volume, moles, and Kelvin. So liter, atmospheres, kelvins, moles are the units on R. A constant always has the units of everything else. Times the temperature, 16, but we got to change it to Kelvin, to 89, divided by the pressure and the volume, 0.982 atmospheres, times the volume of 3.96 liters. And all of that turns out to equal 45.2. I see 2 people shaking their head. 45.2. Make sure we can put this into your calculator right. And it turns out to be grams per mole. Now notice, you have grams here. Atmospheres are going to cancel. Liters are going to cancel. Kelvin's gonna cancel, leaving you grams divided by moles. So the molar mass of this gas would be 45.2 grams per mole, given it occupied that space with that mass and all that information. The ideal gas law gives us quantitative information, it tells us how much is present, which is why it's so much more useful than these other ones. Now, how would we find out what the volume of the gas is at STP? We need a new volume, right? So now all of a sudden we have a new set of conditions. We have new temperature, new pressure, and we want a new volume. So what should we do? How? I mean, we could technically still use this ideal gas law. But what do we solve for? Volume. Okay? But what? We don't really know, well, we could figure out moles now, couldn't we? If we know the molar mass, because we have grams and we have the molar mass. Okay, and solve for that. Or, what's another way? Think about what we were doing yesterday. Or what we actually just did first thing today. Use the combined one. P1 V1 over T1 is equal to P2 V2 over T2. To where our initial pressure, 0.982 atmospheres, our initial volume of 3.96 liters, our initial temperature of 290, 289 is going to equal, what's the pressure at STP in atmospheres? 1 atmosphere. We're looking for the new volume, P1 V1 over T1. The new temperature, what's the temperature at STP? 273. So the reality is we just got to bring the 273 up here because we don't really have to divide by 1. So the volume at STP equals is that what? 3.67? Okay, I'm seeing another head shaking, yes, 3.67 liters. Okay, so when you're going from one set of conditions to another, we're going to use the combined gas law. If we just have one set of conditions, we use the ideal gas law. Now, we could have used the ideal gas law here. Now, this is the way I think is the easiest to see, most straightforward way to do it. But we could also use the ideal gas law. We now know what the molar mass is. So if I use molar mass as GERD over PIV, 45.2 grams per mole is equal to my 7.4 grams. Because changing temperature and pressure doesn't change how many moles or how many grams are going to be present. It's still a closed container, same number. Okay? GERD, 0.0821. The temperature is now at STP, so the temperature is going to be 273 over 1 atmosphere, and we're looking for volume. So, how do we rearrange this algebraically?
Divided by 45, that whole thing by 45.2.
And where does the V go?
You would multiply, so it would just be, you just bring it over.
You multiply both sides by V, and then divide by here, so really these two are just going to switch. So V is going to equal 7 point, you don't really have to rewrite this whole thing over again. And I guarantee it's gonna come out to the same number. But you can plug it in just to verify.
Yes.
3.67. Okay, so there's really gonna be more than one way to solve these problems. It's just whatever one makes the most sense to you. Okay? Because they're all kind of related to one another. The whole idea of pressure, volume, moles, they're all relational, they're all proportional to each other. We good with all that? So we can just plug in, and tomorrow, Thursday, we're gonna just spend some time working some practice problems of these, just making sure that we know how to do, Boyles, Charles, Gay-Lussac's combined, and some of the ideal gas law stuff. Okay, so we'll do some practice, but then we need to really get into some stoichiometry. But let's keep moving forward then. Okay, this is just really important. So we can use 22.4 if we're ever at SDP. That's going to be a good conversion factor for us. Okay, now looking at this, what is the volume of 1 mole of nitrogen at SDP? 22.4. Okay, but then how many liters of gas at SDP do you have if you have 13.6 grams? Well, the 22.4 is what unit? I know, but what's the unit on it? Liters per mole. So, but if I'm giving grams, how I need to get to liters, what do I have to do first?
The molar mass.
I gotta find the molar mass, I gotta convert to moles, right? Then I can use 22.4 because it's at SDP. Now this only works at SDP. If you're at other conditions, you gotta use the ideal gas law. Okay? So, we could go 13.6 grams. What would be the molar mass of N2?
Can't read that one. 14.01 for 1, so 28.2.
I'm very good without a calculator. I'm impressed. Woohoo! Look at there. Okay, times 1 mole over 28.0136, which really is 28.02. Okay? I'm not sure how far out they're carrying everything. That's pretty far out. Okay? Times 22.4. Okay? So you just multiply all that out and you end up getting 10.9 liters. So the key is that the 22.4 is now going to be a conversion factor between gas volume and moles. Okay? All chemistry is really conversion factors. I have something for you. And unfortunately, right when I put it in the copier, something got on the main thing, so there's a little bit of a smudge on it, which bothers me. This is what I refer to as my stoichiometry roadmap. I don't think I gave this to you earlier. Y'all seen this before? No? Okay, good. This is what I call my stoichiometry roadmap. And this is where we're going to get into on Thursday, and this is kind of the same type of problem here with the stoichiometry of just converting grams to liters. But when I'm going somewhere, I have a horrible sense of direction. My male pride, I used to fight it. I used to, I'll get there, but I got lost so many times that I have now just come to the realization that, okay, I'm direction lexic, which means that I get things backwards. If I think I need to go left, I probably need to go right. Okay? Now the problem with that is I've recognized that that's a problem. So now I say, man, I really think I should turn left. That means I probably should go right. But then I say, well, but then I'm thinking I should go right, so maybe I should go back left, so sometimes I just go straight. And so, I get lost with GPS. I mean, it's just crazy. Anyway, my wife has total freedom to always say, we're getting off here, this is our exit, you know, just, you're gonna go to the left. Why are you in the right lane? I mean, it's just this. So I have to have a map. Some of y'all get lost on where to start, where to go on stoichiometry problems. Some of y'all are direction lexic when it comes to, you know, where do you start, where do you end, what should I do next? And you get things backwards. This kind of helps guide where we're going to go. Everything on my left is what I'm given. Okay? I could be given atoms or molecules. I could be given grams. We're going to do solution volume next. It's just something to look forward to. Now we have a gas volume at STP, and we could be given a gas volume not at STP. But the first step of any stoichiometry problem is always take my given and convert it to moles. Because here, the balanced equation just gives us a mole ratio. Now so far we did mass to moles to moles to mass. We could have done atoms. I could have given you atoms and molecules and done the exact same thing. We just would have used Avogadro's number to convert to moles instead of the molar mass. Once you get to moles here, you use the coefficients of the balanced equation, the mole ratio, to go to moles of unknown. And then from there, we go back to whatever we need using the same conversion factor, just the opposite way. Now, what we're adding in are gases. So if it's at STP, we can convert from a gas volume, 10 liters of gas at STP, we can just use 22.4 to know how many moles we have. If we're not at STP, we use the ideal gas law, where N is going to be equal to PV over RT. But the step is always converted to moles. So these, what we're really kind of learning at the beginning is how do we convert to moles? Because that's what we really want to know how to do with the stoichiometry. I know that's the burning desire in your heart, is to be able to do these gas law stoichiometry problems. Because it's going to help you the rest of your life of knowing. It's not, but remember, we're in the weight room for our brain, we're learning how to think. So we're just using something very cool like chemistry to do it. All right? So this is just, these are the conversion factors on how you get from this to moles. Okay? Avogadro's number, the molar mass. We're going to find the concentration, the molarity here, that's next. 22.4 for the ideal gas law. Now with the ideal gas law, you actually have to do it in 2 steps. You can't just do the big long parenthesis, 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 parenthesis. You got to stop, get moles, then go moles to mass, or moles to whatever. Okay? But all the other ones you can just kind of keep going because they're all just conversion factors. Does that make sense to you? Do you understand how this thing works? Hopefully it gives you a little bit of a visual on where am I starting, where am I going, what do I need to do, how do I get there? Okay, it's just the stepwise process. All we're doing is adding in different conversion factors. All right. I feel like we probably ought to do one, but we're so close on time. But at the same time, we can't just quit. Okay? So here's this one. Now I'm assuming you could do this. We're going to do the exact same thing. We're just going to use 32 grams for this times the 22.4. All right. Now, I do have time in 2 minutes to explain how to do these types of stoichiometry problems. A gas volume to gas volume. Avogadro's principle says equal volumes contain the same number of moles. So if I know I need 2 moles of hydrogen for every 1 mole of oxygen to make water, that means I got to have twice the volume that I do of oxygen. Twice the volume, 20 liters, will combine with 10 liters in the right H2O ratio. Equal volumes. So gas volumes This here, 4, tells me I have 4 moles, I have 4 molecules, but I also have 4 liters. I have 4 of anything, 4, equal volumes. I'm gonna need 7/4 as much oxygen to combine with it. In other words, the volumes combine in the exact same ratio as the coefficients, just like moles. Volume and moles are directly proportional. So gas volume to gas volume is really just moles to moles. You just use the ratio and you're done. And we'll start in on doing practice problems like that on Thursday, and then we'll kind of go through and we'll end up focusing in on all of the stoichiometry. Did you sign?